For this video, we're going to be taking a look at electrophilic aromatic substitutions and 3 general steps that can be used to apply for any of the mechanisms. And then we'll later take a look at specifically friedel alkylation and how it utilizes these 3 steps. So, to begin this video, I'd like to just talk about what an Eas reaction is and what's occurring. So we're going to be starting with an aromatic ring. For this general example, I'm starting with a benzene molecule and I'm going to just be adding on an R group. This is called friedel alkylation. So we know that aromatic rings are very stable. So normally we can't do things like SN2, SN1, but a reaction that we can do is EAS. And so what's happening, if we look above here, we'll see that the first thing that we need to do is create something that's super electrophilic. If something's super electrophilic, then the aromatic ring will actually temporarily break its aromaticity and it will go and attack the superelectrophile. So that's step 2. One of the pi bonds goes and attacks the superelectrophile. And then the last thing that happens is there is a way for us to restore our aromaticity in the ring, which is super favorable because we know that aromatic rings definitely prefer to have that aromaticity, right? It makes it a lot more stable. So what we're going to do for our third step is we're actually going to take or kick out one of the hydrogens so that we can restore that aromaticity. Awesome. So looking at friedel alkylation specifically, we'll see that the first thing it will do is generate our superelectrophile. So we'll have our alkyl halide go and attack AlCl3. And drawing in our partial charges for this is really beneficial to understand what's happening. So chlorine's nucleophilic, aluminum is electrophilic. So this is going to attack. And then, we have a positive charge on that chlorine and a negative charge on this aluminum. And this right here is our superelectrophile. We know that chlorine is really electronegative, so it having a positive charge is very unstable, which makes this whole thing very electrophilic. So our second step is that a pi bond is going to come and attack. So I'll redraw our complex here. And something interesting happens. If you notice, we're actually going to be attacking the R instead of the chlorine. And the reason for this is that our chlorine is going to be much happier if it just gets its lone pairs back. So by us attacking, or by the pi bond attacking the R, the chlorine is going to get its lone pairs back, and now it's going to be really stable again. So this will give us there's a hydrogen right there, and there's a positive charge on that carbon. And then our byproduct is, okay, and so here, our aluminum still has a negative charge, so it's not very stable, so we're actually going to break a sigma bond between the aluminum and the chloride, and that's going to come attack this hydrogen, and this hydrogen is going to kick off, and it's going to restore the aromaticity by forming a pi bond. So we add on our R group, and then the other 2 byproducts are HCl and AlCl3. So going back here, this is the third step where we restore aromaticity. So just another overall review, we have the first thing, we're generating our superelectrophile. This is our first step. Second step, our pi bond is going to attack our superelectrophile, and our third step, we're going to restore aromaticity by kicking off that hydrogen and forming a pi bond with it. So these 3 steps can be used for all other EAS reactions, so I definitely encourage you to go through other EAS mechanisms and try to use the same 3-step formula. Hope it helped.